Okay, imagine this right. You've got a cylinder, and it's at the very bottom of its stroke. The piston starts moving up. What's pulling the air and fuel in? Is the engine actually sucking? I mean, we say that all the time, but the reality is a bit more nuanced, isn't it? We'll have to dig into that another time.
Absolutely.
But for now, welcome to Einstein Motors. This is where we break down the science behind everything automotive. We'll unpack the complexities so you don't have to. And let's be clear, engines don't suck air in, they create a lower pressure. Today we are diving deep into something you might encounter when you're modifying an engine. Compression ratios, and more specifically, the difference between static and dynamic compression. You reached out to us with some great questions about calculating compression and how camshaft timing can affect it, and that is exactly what we're going to unpack.
Yeah, and it's great you have a solid grasp on that basic concept of static compression, because that's really the foundation, the inherent capability of the engine to compress, determined by its physical components and how it was machined during the build. It's kind of like the theoretical maximum compression it can achieve.
Right.
You can think of it as a ratio. You've got the volume of the cylinder when the piston's all the way down, at bottom dead center, BDC. Then you compare that to the much smaller volume left when the piston's all the way up, at top dead center, TDC, with the valves closed, of course.
Okay.
It all comes down to the engine's geometry, the dimensions, and how it's all put together.
Exactly. And you're working on a 350 Chevy build, right? You've got aluminum flat top pistons sitting about 0.024 inches below the deck at TDC, 64cc Vortec 062 heads, and a Crane 282 camshaft. So you're trying to figure out your static compression. You mentioned that you're doing your calculations based on the valves being closed, and that's a good starting point, but that's where things get really interesting. You see, that camshaft timing throws a bit of a wrench into the equation.
Right, a huge wrench. The key thing to remember here is that you don't start building serious compression until that intake valve closes. That's what creates the sealed chamber.
Makes sense.
If the intake valve's hanging open, well, there's nothing to compress. So the timing of that intake valve closing becomes absolutely crucial. And in almost all modern four-stroke engines, especially the ones designed for performance, that intake valve doesn't slam shut right at BDC. It usually closes some degrees after the piston has already started moving up on the compression stroke. We're talking about after bottom dead center, ABDC.
Oh, okay, so it's closing late.
Exactly.
And with your Crane 282 camshaft, you said it closes at 34 degrees ABDC. That's a lot later than BDC. So how does that late closing affect the actual compression the engine makes?
Well, it's a bit of a trade-off, right? Because if you keep that intake valve open longer, past BDC, it actually lets you fill the cylinder better at high RPMs. That gives you more power at the top end. But during that initial part of the compression stroke, while the intake valve is still open, some of that fresh air and fuel mixture can actually escape back into the intake. We call this blowback. And what it does is it reduces the pressure you can build at lower engine speeds. So it ends up lowering the dynamic compression ratio.
So just to clarify, static compression is the theoretical one, the number we get from the engine's physical dimensions. Dynamic compression is what's actually happening inside the cylinder as the engine's running, taking into account the timing of those valves. Is that right?
You got it. Dynamic compression, it's the real deal, the actual pressure in the cylinders. And as you mentioned, it's not a fixed value like static compression. It changes based on things like camshaft timing. And you could bet that dynamic compression is always lower than static, because you never get to compress that full cylinder volume at BDC.
Okay, so a more aggressive camshaft profile, one that closes the intake valve later ABDC, will give you a lower dynamic compression. That makes sense. It's like you're starting the compression process with less air and fuel trapped in the cylinder.
You can picture it that way, yeah. And while the intake closing point has the biggest impact on dynamic compression, there are other factors to consider too.
What?
Well, you mentioned connecting rod length and crankshaft stroke.
Yeah.
And they do play a role. Those dimensions affect where the piston is in the cylinder at the exact moment that intake valve closes. So, for instance, with the same stroke, if you have a longer connecting rod, the piston will be higher up in the cylinder at a specific crank angle compared to a shorter rod.
Got it. So it's a bit of a dance between the fixed geometry of the engine's bottom end and the dynamic timing of the valvetrain. Now, I remember reading somewhere that dynamic compression can be a good indicator of what octane fuel an engine needs. Is there any truth to that?
You're spot on. Understanding dynamic compression is super helpful for predicting the right octane rating, because it tells you more about the actual pressures and temperatures inside the cylinder when combustion happens. That's when you run into problems like detonation or knocking. And a good rule of thumb is that most Pump gas, the good stuff, works well in engines with a dynamic compression ratio of around 8:1.
That's a handy benchmark.
Absolutely. And the info you sent over included this great example from KB Pistons. They talk about a Chevy engine with a 10.1 static compression ratio. Pretty high, right? 3.48-inch stroke, 6-inch rods, and a camshaft that closes the intake valve super late at 90 degrees ABDC. That's aggressive.
Yeah, super aggressive.
And because of that late closure, the dynamic compression drops down to 6.17.11. That's low enough that you could probably run 80 octane fuel in that engine without any problems.
Wow.
But here's the flip side. If you wanted to hit that 8.1 dynamic compression with those same rods, stroke, and that crazy late 90-degree intake closing, you need a static compression ratio of around 13.2 to 1. That's incredibly high.
So cam timing really does make a huge difference. You can have a high static compression, but still run regular fuel if the intake valve closes late enough.
Exactly. But remember, we've been talking about how a late intake closing usually lowers dynamic compression. But there are a few other things that can actually increase the amount of air and fuel trapped in the cylinder.
Oh, really? What kind of things?
So things like well-designed intake ports, the way exhaust pulses can help scavenge the cylinders, and a phenomenon called inertia supercharging, where the momentum of the incoming air and fuel helps pack more into the cylinder. All of these things, if they're optimized just right, can result in a higher tracked volume than you'd expect based on static volume alone.
Interesting.
But in most cases, and especially with those camshafts designed for high RPM power, the late intake closing has a much bigger impact and lowers dynamic compression overall.
Okay, so we've got static compression, the ideal based on the engine's design, and dynamic compression, the reality of what happens when the engine is running, which is heavily affected by that intake valve closing. But how do you actually calculate dynamic compression? Is there a specific formula that enthusiasts can use?
Well, there's no magic formula where you just plug in numbers and get an exact dynamic compression ratio. It's a bit more complicated than that.
Okay.
It involves figuring out the absolute cylinder pressure.
Yeah.
You mentioned a relationship earlier. Dynamic pressure equals dynamic ratio raised to the power of gamma, multiplied by atmospheric pressure.
Right.
And gamma, that Greek letter, is called the polytropic index. It usually sits somewhere between 1.2 and 1.3, and it accounts for the changes in heat that happen inside the cylinder during compression. Because not only does the temperature increase because of the compression itself, you also lose some heat to the cylinder walls and piston. So dynamic compression is more than just volumes. It's about pressure. It's about heat. It's about when that cylinder is actually sealed.
So gamma is like a correction factor that acknowledges that real-world engines aren't perfectly efficient.
Exactly. In a perfect world, with no heat transfer, what we call adiabatic conditions, gamma would be around 1.4. But in a real engine, we use a lower number because there's always some heat loss. Here's an example to illustrate this. Imagine an engine with a 10.1 static compression ratio, but only a 7.5.1 dynamic ratio. If you do the math, 7.5 raised to the power of 1.3 times the atmospheric pressure, you get a cylinder pressure of about 13.7 bar above atmospheric. That shows you that it's not just about the volume ratio, it's about the final pressure, which depends on when the effective compression starts due to valve timing and how much heat is lost. And this goes back to the idea that you can have a high static compression with a late intake closing and end up with a similar dynamic compression to an engine with lower static compression and earlier closing.
Okay, so it's more about the whole picture. It takes into account the engine's dimensions and the things happening inside. And this brings us back to your 350 Chevy build. You're aiming for 10.1 static compression. How does understanding dynamic compression, especially with that Crane 282 cam and its 34-degree ABDC closing, change your approach?
Well, thinking about your specific build, that 10.1 static compression target needs to be seen in light of that Crane 282 camshaft. Since the intake valve is closing relatively late at 34 degrees ABDC, the actual dynamic compression you'll get will be lower than 10.1. And practically speaking, this is a good thing when it comes to using pump gas. That late closure actually helps bleed off some of the pressure at low RPMs. So compared to an engine with the same 10.1 static compression but earlier intake closing, yours will be less likely to knock on regular fuel.
So even though you're building for a 10.1 static compression ratio, the dynamic compression tells you that you've got a little bit of leeway with fuel because of that camshaft choice.
You got it. The static ratio is important for the engine's design and build. But dynamic compression gives you a much better understanding of how combustion happens in real life. And that camshaft timing, especially that point where the intake valve seals up the chamber, that's what really determines your engine's true effective compression.
So, as our listeners can see, while static compression gives you that fundamental measurement of the engine's design, the dynamic compression ratio is what paints a more realistic picture of what's going on inside the cylinder while the engine's running. And the timing of those valves, especially that intake closing, plays a huge role in the engine's effective compression.
Absolutely. It just goes to show that building an engine isn't just about bolting together parts with the right static dimensions. How those parts interact dynamically, especially the way the camshaft affects cylinder sealing. That's what you need to understand to really grasp the engine's performance and its fuel requirements.
We hope this deep dive has shed some light on the difference between static and dynamic compression and shown you how camshaft selection can really impact your engine build.
It's a crucial concept.
For more in-depth technical explanations and to check out our awesome automotive calculators that can help you with your projects, be sure to follow Einstein Motors on social media or visit our website at einsteinmotors.com.au.
We've got tons of resources to help you out.
Thanks for listening.
See you next time.